So therefore, to get to these very high TeV energies as promised by the title, then you need to come up with some new accelerating techniques. So one suggestion for a linear accelerator could be the compact linear collider, CLIC. It's a linear E plus E minus collider, as we talked about. It's going to reach 3 TeV in center of mass energy, and to reach these energies within a certain distance, that is a distance of, in this case, 50 kilometers, you need an acceleration gradient of 100 megavolts per meter. That is quite a high acceleration gradient, and I think the highest that has been, well, the highest acceleration gradient you can achieve in normal RF acceleration structures is about 20 or 30 megavolts per meter. So, and these have to be superconducting RF cavities.
But if you were to, can I ask?
Yes, sure.
If you were to multiply acceleration gradient with 50 kilometers, if I heard you correctly,
yeah,
would you exceed the 3 TeV by a lot? Or
of course, but you cannot have these 100 megavolts per meter over all the distance.
Okay.
So that is what you're going to see in a minute. What is used to reach these very high energies in these acceleration gradients is this so-called two-beam acceleration principle, which we're going to come back to within a minute. But first I'll just give a visualization of where CLIC would be built. It could be along the Juros at CERN, where the LHC is of this size, and you know the LHC is 27 kilometers in circumference, so, well, it looks quite big to compared with the LHC. So let's look at the two-beam acceleration. In the two-beam acceleration principle, you use what is called a drive beam to accelerate the main beam. The drive beam has there's a very high intensity, so it's also electrons or positrons that you send through these structures, and then you have a lot of deceleration components where it's actually possible to extract the power through these tubes, and we will see that in a minute. And then you can, well, so it's just electromagnetic waves that will be guided through these tubes, and then they'll be sent into these accelerating structures to accelerate the main beam, which has a lower intensity, that is a lower current is going in this beam. So what we will, what happens is actually that what you're going to see now, if this works, that as you maybe saw, the beam was coming here, and that is the drive beam, and then an electromagnetic wave is built up. That is, the wave is called the wake field. It is built up and it is transmitted through this tube into the acceleration structure here. And as you see, the frequency of the structure here is a lot smaller than what it is here. And this so-called power extraction and transfer structure can actually be compared to a very well-known thing. It can be compared to the transformer not this transformer, but the transformer over here, where you have a current and a voltage difference at one side, and you have this coil with well, let's say n S turns. Or actually, let's start here, because this is a primary coil. You have NP turns in one side, and you have NS turns in the other side, and then you have a voltage difference here that can be converted into an induced voltage difference. And now I would like you to try to build such a transformer. As you remember, just try to recall this this figure, and then I'd like you to build a transformer, measure the induced voltage, and compare it to what is the voltage going into the system, and then we should try to calculate what is the voltage, and does this actually agree with the voltage that we measured. And yeah, so I'd like you to build it such that the voltage is increased, going from the primary voltage to the main, to the induced voltage. And I see that you are already doing well. So let's see what happens. You can just ask questions if you want.
Yes, I think that will maybe be necessary.
So I guess you need power.
The power supply is.
So maybe it's maybe you can take it just there. There you go in. Yeah. And of course,
in which order here is that? If you have a preferred order.
Well, you can do it as you like.
Okay.
But so okay. And now maybe you would like to measure what is the voltage difference.
Maybe I will.
It's just a guess.
Yeah.
So you can do that with this.
This one, right?
Yeah, you can do that with this multimeter.
Yeah.
And should it be an alternating or direct current that you send through?
Right. I guess I can. That depends on the power supply. If that's DC, I would have to measure DC. But
so let's go for AC.
Yeah. So is that over here?
Yeah, that's actually over here.
Oh, yeah, I can see.
Because you need, because what happens is that you need to change the current going through such that you get an induced magnetic field going around in this what you would call the magnetic or going through these iron coils.
The change of the field, right?
Yeah. So it's exactly. So what actually happens is that let me just write the equation.
Yes.
So the voltage is given like this.
I'm not sure if I'm doing this right.
So you have to measure the alternating curve, which is done here.
Ah, okay, it makes sense.
Yeah.
It goes up. So now it's like, that would be a good starting point.
Yeah.
9.6 or so.
Yes. And then what would you expect the voltage difference to be over here? So this is the voltage, and this is the number of turns in the coil. And if we write the same equation on the primary side, then it looks like this, and you have the same change of flux. or the same flux.
Magnetic.
So yeah, magnetic flux. So if you divide here the two equations, then these two will disappear.
That's an awesome math.
And you can actually see that.
So I'm interested in Vs, right? The secondary voltage.
Exactly.
So
yes.
that would be.
And you need the secondary voltage to be higher than the primary voltage. And how can you do that?
By having more windings in the secondary coil.
Exactly.
But that.
And how is it now?
Actually, now I think I thought I was smart, but maybe actually that was not smart because now I have less windings in the secondary coil.
But that is very easy.
Switch is.
Okay.
So now I would expect it to be 4 times larger because there's 1,000 windings in this one.
Yes.
And 215 the primary.
Yes.
So how about we check that?
Yeah. And, we have another one here, so you can check it.
Great.
At the same time.
I have to give you compliments for being an excellent teacher. Everything is prepared here.
Thank you very much. Okay.
So
Does
the
that
primary meter, or the meter that's measuring primary voltage, I have 9.55.
Yeah. So P 9.5
and on
6.
the secondary reads 35.45 or so.
Okay. And this was 5. Okay. And is that what you would expect?
I guess it would be
4. So 4 times 9.
So we should have been around 38, but
Yes.
maybe because of dissipated forces, it's clear, it's natural that it's still off.
So you saw here that we have this drive beam with a high intensity, and then we have this main beam up here. And what would correspond to the number of turns in this case?
The frequency.
Yeah,
Of
the frequency would be a very nice suggestion. So the frequency here is lower, and the frequency up here is higher, and that way we can extract the electric field, and we can get a very, very high voltage difference between each step here. So you can see the combination of these beams going into a high frequency in this illustration, where actually the bunches of beams are not electrons or positrons, but they are small lemmings walking in these bunches, and the separation here is a bit larger than here, and the difference here is such that when the lemmings go around here, the next bunches go just in between, and then they go around this large combiner rings, and again, as you'll see, there's a perfect fit that will make the lemmings go not exactly in between, but like this, such that when the next lemmings come here, you combine the electrons again, and after 4 turns, you will see a perfect combination of bunches, and the frequency will be increased by a factor of how much?
There.
So first we increase the factor by the frequency by a factor of 2,
Yeah.
and afterwards
5 or 4. I don't know.
by a factor of 4. So that must be a factor of 8 in total.